Good morning everyone. In the next few classes, we shall focus our attention on the numerical development of solution of system of linear equations. The system of linear equations in n variables can be written in the form a11 x1 plus a12 x2 plus etc. plus a1n xn equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn is b2, and so on. The nth equation is an1 x1 plus an2 x2 plus etc. plus ann xn equal to bn. Here the aij's and the bj's, they are all real numbers, and the xi's are the unknowns to be determined. And we see that the system of equations can be represented in matrix form as Ax is equal to B, where A is an n cross n matrix and X is an n cross 1 vector and B is an n cross 1 vector, where A can be given by a11, a12 etc. a1n, a21, a22 etc. a2n, and so on, an1, an2 etc. ann. X vector is given by x1, x2 etc. xn, and the right hand side vector B has n components b1, b2 etc. bn. So, our objective is now to discuss numerical aspects of solving the system of equations given in matrix form, say Ax is equal to B. So, let us see some simple cases where we can immediately present the solution of such a system. Suppose the system of equations Ax is equal to B is such that A is a diagonal matrix, namely A has elements d1, d2 etc. dn along the diagonal, and the rest of the entries in the matrix are all zeros. So, A has entries only along the diagonal. Then in that case, the system Ax is equal to B will be such that A multiplied by the column vector x1, x2 etc. xn will be b1, b2 etc. bn, and we observe that we have d1 into x1 is b1. So, x1 is b1 by d1. The next equation gives you d2 into x2 is b2, and so x2 is b2 by d2, and so on. The last equation gives you dn into xn is bn, and therefore xn is bn by dn. So, in general xi is bi divided by di, and this is for I is equal to 1, 2, 3 etc. up to n. So, if A is a diagonal matrix and you are asked to solve the system Ax is equal to B, then the solution is immediate. That is a very special case. Let us consider another case where, say, A is a lower triangular matrix. So, L is of the form L11 0 etc. 0, L21, L22, and then zeros. L31, L32, L33, 0, 0, etc. And the last equation will be Ln1, Ln2, Ln3, etc., Lnn. So, this is your matrix A. It is a lower triangular matrix. So, I have to solve the system Ax is equal to B, or in other words I have to solve the system Lx equal to B. So, that will give me this L multiplied by the column vector x1, x2, etc., xn to be equated to the vector b1, b2, etc., bn. So, my system is Lx is equal to B, and it is written in this form. So, we observe immediately that the first equation is L11 into x1, and that is B1. That gives you what x1 is, namely B1 by L11. Then the second equation gives you L21 into x1 plus L22 into x2 is B2. You already have computed x1 here. So, this gives you x2 to be equal to 1 by L22 multiplied by B2 minus L21 into x1. Let us solve from the third equation. What is x3? So, L31 x1 plus L32 x2 plus L33 x3 is B3. So, that immediately gives you x3, because you already have computed x1 and x2 from the first two equations. So, you have B3 to be given by 1 by L33 multiplied by B3 minus. So, this gives you x3 as 1 by L33 into B3 minus L31 x1 minus L32 into x2. So, it is clear how we can get the successive unknowns, and so finally we have from the last equation, which is Ln1 x1 plus Ln2 x2 plus etc. plus Lnn xn equal to Bn, and this will give you xn to be equal to 1 by Lnn into Bn minus Ln1 x1 minus Ln2 x2 etc. minus Ln n minus 1 into x n minus 1. So, you have computed all the components of the unknown vector x, namely x1, x2, etc., xn. How did you do it? You obtained x1, you substituted in the next equation. So, you moved forward to the next equation, got your x2 with the knowledge of x1. Then you further moved forwards to the third equation. With the knowledge of x1 and x2, you computed x3 and so on. You moved forward to the last equation, and with the knowledge of x1, x2, etc., xn minus 1, you computed the value of xn, and all the unknowns are determined. This method is called the forward substitution method. And therefore, if you have a system of linear equations in which the coefficient matrix A is a lower triangular matrix, then its solution can immediately be obtained using forward substitution method, as has been explained here. So, let us now see what happens if A is an upper triangular matrix. Let us consider A to be an upper triangular matrix U. given by u is equal to u11, u12, u13 and so on u1n, 0, u22, u23 and so on u2n, 0, 0, u33, u34 etc. u3n and so on, and the last equation will have 0 everywhere and the diagonal entry will be unn. So, U is an upper triangular matrix and you now have to solve the system Ux is equal to B. So, this multiplied by x1, x2, x3 etc. xn should be equal to B1, B2 and so on Bn. So, now you observe that you should go backward because you have an equation of the form unn xn is Bn, which will immediately give you what xn is, namely it is Bn by unn. And then you go backward and look at the equation which appears in the last but one row. So, that gives you u, where does it appear? It will appear in the n minus 1th row and the entry here and the entry in the diagonal will be non-zero and the other entries will all be 0. So, let us see what happens in the case when we go to the third equation. So, typically a third equation will give you u33 multiplied by x3 plus u34 x4 plus etc. plus u3n xn, and that will be B3. But you have already obtained xn, xn minus 1 etc. etc. up to x4 because you have moved backwards. And so, this will immediately tell you what x3 is, namely x3 will be 1 by u33 multiplied by B3 minus u34 x4 and so on minus u3n xn. And so, the first equation, if I move backward and reach the first equation, that is u11 x1 plus u12 x2 plus etc. plus u1n xn, and that is B1. You have computed all these coefficients x2, x3 etc. xn. So, you require x1 and the first equation will give you x1 to be 1 by u11 into B1 minus u12 x2 etc. minus u1n xn. So, you have been able to obtain the unknowns by moving backward from the last row of the system of equations to the first row, and so this is referred to as backward substitution. And therefore, if you are given a system of equations in the form Ax is equal to B, where A is an upper triangular matrix, then immediately its solution can be obtained by backward substitution method. So, we may not come across such simple equations all the time, namely the coefficient matrix is a diagonal matrix or an upper triangular matrix or a lower triangular matrix. We will have to solve a system of equations of the form Ax is equal to B, where A is neither a diagonal matrix nor an upper triangular matrix nor a lower triangular matrix. But these suggest that if we can reduce the coefficient matrix A of the given system to a diagonal matrix or either a lower triangular or an upper triangular matrix, then the solution can immediately be obtained. So, we now look for some general purpose algorithms that will help us to solve a system of equations Ax is equal to b. So, our objective is going to be discuss numerical algorithms that will help us to solve a system of equations, and then discuss the errors associated with the computed solution and study methods for controlling and reducing these errors, and finally see if we can understand some iterative methods for solving such system of equations. So, our system is something like this. We have n equations in n unknowns which can be put in the matrix form, namely Ax is equal to b. So, while deriving such numerical algorithms, the elementary operations are very useful to us. So, we look at what are these elementary operations, and using elementary operations we try to develop some numerical algorithms for solution of a system of equations. So, let us write down what are the elementary operations that we will use in our computations. So, it is exchange of two equations in the given system. Namely, I take the ith equation of the system and exchange it with the jth equation. For example, I can take the first equation and exchange it with the nth equation, namely put the first equation here and the nth equation as the first equation. Secondly, multiplying an equation by a non-zero scalar. Namely, I take the equation say Ej, multiply it by lambda and replace Ej by lambda Ej, where lambda is a scalar. Multiplying an equation by a scalar which is non-zero and adding it to another equation. Namely, I consider the equation Ej and multiply an equation Ei by lambda and adding it to Ej and replacing this Ej by lambda Ei plus Ej. So, any one of these operations is called an elementary operation. Now, the question is, when we perform such elementary operations on a system of equations like this, then if we determine the solution of the new system, will the solution be different from the solution of the original system? The answer is no, and it is given by the following result, which says if a system of equations is obtained from another system by a finite sequence of elementary operations, then the two systems are equivalent. What does that mean? I have a system Ax is equal to B that is given to me, and I make use of a finite sequence of these elementary operations, and I obtain a new system, namely say A is changed to some A tilde, the unknown vector is x, and B is changed to B tilde. So, this new system and the old system are equivalent to each other. That is what the theorem says. And we write A is equivalent to A tilde when elementary operations are applied to A, and we have a finite sequence of elementary operations that has converted A to A tilde. So, the system obtained after finite sequence of elementary operations is equivalent to the original system, and therefore, if we solve the new system and obtain its solution, then the solution of this system is the same as the solution of the original system. That is what this result says. So, given a system Ax is equal to B, what is it that we have done all along? We will see if A is a non-singular matrix, namely determinant of A is different from 0. Then A inverse exists, and therefore, we will write down the solution as A inverse into B. This is what we have been doing all along. So, given a system, if A inverse is available, then use this where the solution x is given by A inverse B and obtain the solution. If suppose A inverse is not available to you, then do not try to obtain A inverse, because there are very efficient procedures which are available for solving a system of equations of the form Ax is equal to B, and we will derive or we will develop these efficient algorithms now, so that you can make use of them in solving a system of equations Ax is equal to B. And these methods belong to two categories of methods, namely they belong to either direct methods or iterative methods. And indirect methods, we will discuss methods such as decomposition methods and Gauss elimination method and Gauss-Jordan method. Whereas, in the case of iterative methods, we shall consider methods such as Gauss, Jacobi and Gauss-Seidel methods. So, these are different methods that we are going to develop in the next few classes, and try to see how these methods can be used in solving a system of equations Ax is equal to B. Along with that, we are also going to discuss the errors associated with the computed solution and see ways by means of which we can control the error and reduce this error. So, let us now look into the decomposition methods first. We now consider decomposition method, which is a direct method for solving a system of equations Ax is equal to B. So, given a system Ax is equal to B, we would like to develop a method called decomposition method, by means of which the system can be solved. So, if a matrix A can be factored or decomposed in the form A is equal to L into U, where L is a lower triangular matrix and U is an upper triangular matrix, then in that case solving the system Ax is equal to B is equivalent to solving Lux is equal to B, because A can be factored in the form L into U, where L is lower triangular and U is upper triangular matrix. This suggests that if I set Ux is equal to Z, then this Lux is equal to B becomes Lz equal to B. So, let us see how we can obtain our solution X. In this Lz equal to B, we know what B is because we have given the system Ax is equal to B. So, the right hand side is a known vector and Z is an unknown. I do not know what Z is, but L is a lower triangular matrix because we have been able to factor A in the form L into U, where L is lower triangular. And so, we have now a system Lz equal to P with coefficient matrix as a lower triangular matrix. We have already discussed. In that case, the system's solution can be immediately written down by what method? By forward substitution method, because it is a lower triangular coefficient matrix. So, solve for Z using forward substitution. So, what will you get? You will get what Z is. Once you know Z, you substitute here. So, you now can solve Ux is equal to Z. The only unknown is this vector x. You know what the matrix U is, it is an upper triangular matrix, and Z has just now been computed by forward substitution method. So, the unknown vector is x. So, at this stage you solve for x by what method? The system is Ux is equal to Z, where the coefficient matrix is an upper triangular matrix, and therefore, you can solve for x by back substitution. So, what have you got? You now have the solution, namely the unknown vector x has been obtained, because you are asked to solve the system Ax is equal to B. So, you should be in a position to factor the matrix A in the form L into U, or decompose the matrix as a product of two matrices L and U, where L is lower triangular and U is upper triangular. If that is done, then the solution of the system can immediately be obtained by first doing forward substitution and obtaining Z from the system Lz equal to B, and then using backward substitution method and solving the system Ux is equal to Z. Suppose say we are able to factor A in the form L into U, and in case that matrix L is a unit lower triangular matrix, then you say that the method is Doolittle method. Namely, you factorize A in the form L into U with L as a unit lower triangular matrix, and then solve the system by forward substitution followed by backward substitution. Then you have used a Doolittle method for solving the system of equations. Secondly, if U is an upper triangular, or U is a unit upper triangular matrix. Then the method is called Kraut's method. Namely, you factorize A in the form L into U with U as a unit upper triangular matrix. And thirdly, if you can write down A in the form L into L transpose, where L is a lower triangular matrix, then solve the system of equations. The resulting method is called Cholesky's method. Is called Cholesky's method. The question now is, if we can decompose the matrix in the form L into U, then we can apply forward substitution followed by back substitution to obtain the solution of the system of equations. Is it always possible to factorize A in the form L into U? The following result gives us a sufficient condition under which a matrix A can be decomposed in the form L into U. So, let us write down the sufficient condition. It is given by the result that if all the leading principal minors of the matrix A of a square matrix A are non-singular, then A can be decomposed in the form A is equal to L into U. So, what do you mean by leading principal minors of a square matrix A are non-singular? Let us take an example and understand this. Let us consider the matrix A as this. It is a 3 by 3 matrix. The principal leading minor of order 1 is this entry. So, it is positive. Then the principal leading minor of order 2 is determinant of 12, 4, 4, 7, and that is 84 minus 16, which is again positive. And the principal leading minor of order 3 is determinant of the matrix A, because A is a 3 cross 3 matrix. So, determinant of 12, 4 minus 1, 4, 7, 1, minus 1, 1, 6. So, let us evaluate the determinant. That gives you 12 into 42 minus 1 minus 4 into 24 plus 1 and minus 1 into 4 plus 7. So, that turns out to be, so I shall write down here 12 into 41 minus 4 into 25 minus 1 into 11. So, it is 492 minus 111, which is again greater than 0, and we observe that all the leading principal minors, namely principal minors of order 1, order 2 and order 3 are all positive, and therefore, all the leading principal minors are non-singular, and therefore, the given matrix A is such that it can be decomposed in the form L into U, or A has a decomposition in the form LU. So, we will given a system Ax is equal to B, and we will check whether the coefficient matrix satisfies this sufficient condition, and then we decompose the matrix A in the form LU and either apply a Doolittle decomposition or a Kraut's decomposition, and then solve the system by forward substitution followed by backward substitution. And then we will focus on the other case, namely when A can be decomposed in the form L into L transpose. Is it always possible? The result says if A is a real positive definite matrix, then A has a unique factorization in the form A is equal to L into L transpose, where L is a lower triangular matrix with positive diagonal. So, what are the conditions which are given? A is a real, so it is also a symmetric matrix. A is a real, symmetric, positive definite matrix. Then A has a unique factorization of the form L into L transpose. What is L? L is a lower triangular matrix, and it has the property that the diagonal elements in L are positive. So, we understand when we are given that A is a real matrix, so all its entries are real. And what do you mean by A is a symmetric matrix? A must be equal to A transpose, then it is a symmetric matrix. And then what do we mean by a positive definite matrix? So, let us give the definition of a positive definite matrix. So, a matrix A, a square matrix A is said to be positive definite. So, an n cross n matrix A is positive definite if x star A x is greater than 0 for any non-zero vector x. What is x star? X star is transpose of the conjugate. So, if this condition is satisfied, namely take a non-zero vector x, and if x star A into x is greater than 0 for any non-zero vector x, then you say that A is a positive definite matrix. And we list down the properties of these positive definite matrices, namely all the leading principal minors of the matrix A are positive. That is one of the properties that a positive definite matrix possesses. And secondly, all its eigenvalues are positive. So, we observe that the given matrix A that we have taken here has all its leading principal minors to be positive, and so this matrix A is a positive definite matrix. And let us check whether it is a real matrix. Yes. Is it a symmetric matrix? Yes. What do we see? This is A12 and that is A21. This is A13 and this is A31, it is the same as that. And A23 is the same as A23. So, this matrix is also a symmetric matrix. So, it is a real symmetric matrix. In addition, all its leading principal minors are positive, and therefore, the matrix A is a positive definite matrix, and therefore, by this theorem, this matrix A possesses a unique decomposition of the form A is equal to L into L transpose, where L will be a lower triangular matrix and the diagonal entries on this lower triangular matrix will all be positive. So, now that we know the conditions under which A can be decomposed in the form L into U, let us work out some examples and see how the solution of a system Ax is equal to B can be obtained if A can be factored in the form L into U.